I'm going to first set the stage a little bit for this panel, and then we'll have the speakers introduce themselves. So the topic of the panel is tinyML inference software. Where do we go from here? I think everyone that's been following the tinyML space long enough has realized how important software actually is. And we could spend an entire week just kind of deep diving on all the different spots of the software stack. So for this panel, we're going to focus really just kind of on the deployment inference side of the software stack, and we can expand a little bit depending on how the panel goes. But just to constrain things a little bit, that's where we'll focus. And I think that's a particularly interesting area to focus because it's my belief that the people that live in that domain, they feel the most pain, because on one side you have a Cambrian explosion of new hardware devices, all sorts of new platforms, new types of ways of doing computation, and the inference stack's job is to then run across all of these different devices and platforms, and they're changing quite quickly. And on the other side, you have the machine learning frameworks, which continue to evolve. They're getting new state-of-the-art approaches every single day. And in the middle, it's the job of the inference stack to kind of bridge those two very dynamic spaces. So that's very interesting to me, and I think that will be the focus of this panel. So why don't we go ahead and do quick introductions. Pete, would you like to go first?
Sure. Hi, everybody. I'm Pete Warden. I'm the tech lead on the TensorFlow-like Micro project, and I've been lucky enough to work with both Chris and Raziel. So I know we're going to have a really good conversation about all this.
Thanks, Pete. Raziel, do you want to go next?
Oh, hi, I'm Raziel. I've been working on the tinyML for a few years now, part of first Google OKG framework, and then a lot with Pete on TensorFlow Lite, and then I also work with Chris in TensorFlow, and currently I'm a tech lead at PyTorch.
Thanks, Raziel. TQ?
Yeah, hi everyone, my name is Tianqi CHEN or TQ. So right now I'm an assistant professor at CMU, and I'm also a CTO of OctoML. So I've worked on several machine learning systems. More recently, I've been working on Apache TVM, which is a compilation framework that helps us to compile machine learning models onto various devices. And we're also actively looking into this micro TVM project, which is specifically how can we improve tinyML compilation and optimization.
Thanks, TQ. Chris?
Everyone, I'm Chris. I lead the hardware and software teams at SiFive. We're pushing state-of-the-art of RISC-V processors and many other things, including AI workloads forward. Beyond that, I'm mostly just a compiler nerd, like runtimes, compilers, making things go fast and efficient.
Great. All right. Yeah. So this is a really fantastic panel, and I'm quite excited the chance to listen to everyone here today. And thank you so much for agreeing to be part of this. Okay. So to set the stage, I talked a little bit about we're focusing on the kind of the ML inference side of tinyML, the ML inference software. So I would like each panelist, if they had to rate the current state of the world from 1 to 10, 10 being things are, the best they could possibly be, 0 and 1 being nothing works. So how would you rate the state of the world today? Chris?
You just want a number, or you want an explanation to it?
Just a number. We'll get the sample, and then we'll see the variance, and we'll dive in.
Okay, I give it 3.
3, okay. All right, TQ?
I think it's around 5.
5, all right, excellent. Okay. Raziel?
I'll give it a 4.
4, okay. And Pete?
I'll give it 2.
A 2, all right. Okay.
Nothing works.
Okay, so Pete, I think being the lowest and the most pessimistic, can you say a little bit about why that's your view? Where do you think things are going and what's holding us back?
So I think the biggest thing that's holding us back is you have to understand a lot of different stuff in order to successfully deploy a new model, like a model that you've trained yourself. Most of where we've had our success so far has been like setting up well-lit paths, talking from like TensorFlow like micro, setting up well-lit paths where we've actually tested, where we're people who actually understand like the full stack and understand everything from model architectures, gathering your data, quantizing, exporting, setting up the code so it uses a fairly small amount of memory, like uses the right ops, does the right pre-processing, does the right post-processing on device. Understanding and knowing all that is still something that's required if you want to kind of create an application from scratch. So I've seen very few teams actually, even professional teams be able to do that with, just full stop. So it feels like the tools are really holding us back.
So I get two points. One, if you know people that can do all of those things, please send me your CV because we would like to hire them. But so I'm interested, what do the other panelists think on Pete's comment?
I completely agree with Pete. I think there's AI as a research field is exploding. Like there's new models, new approaches, new techniques, but deployment is what's holding us back. Deploying in all the ways, and I think that it's worst in small embedded scenarios. But deploying any model outside of ResNet or MobileNet is extremely challenging, and that gap between the research and the production deployment is huge.
It's huge.
Yeah, I agree with all that. I guess the reason why I gave it 4 is because at least at this point we know a lot of the things that do not work, like all the things that we've done wrong. I mean, I'm sure there's going to be new things that we're going to get wrong, but I will say, like, when I started, it was like even worse. We managed to get some things working, and it's painful roads to get where we are at now, but at least TFLite Micro has made good progress, and we keep making progress in different parts of the stack in different frameworks. So at least we know what we've done wrong.
So you gave it that. Oh, sorry. Go ahead, TQ.
Yeah, I kind of agree with Raziel in the sense that I think 5 it's in a scale of 10, right? Not in the scale of 5. So that's So like the main reason that I give a 5 is comparing to maybe when 5 years ago when we got started, that's basically no framework that's able to do things on mobile devices, and nowadays there are quite a few options, although they are not perfect. So at least we have seen progress being made, but I agree, like there are a lot of things to be done. Yeah.
Okay. So it sounds like the generous 4s and 5s is because now we know what's broken or what's hard, where before we didn't even know that.
I think also people have been successful, right? So it's not that it's impossible to do things; it's just that it's unnecessarily hard, and it really restricts the it hasn't been democratized yet to use it, right? And so we want to be able to make it so that AI can go everywhere, and to do that, you need the tools to be accessible. You need the translators to not crash. You need be able to bring in sparsity and other new techniques that are happening, but people are able to deploy things when they try hard enough.
And I think that one of the points that you brought here is you're more successful the more that you know about the entire stack, right? Which is not scalable, right? Like for example, for the hardware, like OKG stuff, right? It helped a lot that I knew the stack to come up with the neural network that we will use, right? That will actually, make use of the power and memory in the best way possible, right? But that's a luxury, right? And that is not scalable. We need to be able to let people that are very good at research do research, but give them feedback to do that research more efficiently and targeted to the devices, right? And I think that part is really missing.
So I guess, so to summarize, are we kind of saying that, there is some hope here because there has been success. We've got some good proof of concepts. Things are working, but it's not done in a scalable way. It takes Herculean, black belt, ninja level abilities to actually do this today. And so what's missing is essentially kind of the abstraction layers, and that would enable this to more people.
I think the way I look at it is that we have a lot of the ingredients there. We have a lot of technologies, a lot of different systems made by different groups. The challenge that I see is that we have, on one hand, the paved paths, I think Pete said, for specific use cases. But when you're talking about a researcher or a production team, they may want to be able to deploy against multiple different pieces of hardware. Right, and so saying that you're going to train with one stack and then deploy with 4 other completely different unrelated stacks just becomes really untenable. And you see this in mobile, you see this particularly in IoT space, but even in the larger scale deployments, you talk about data center inference and things like this, it's still a mess. And we have these different islands of technologies that are not super well integrated, and I think that's one of the challenges that's holding us back.
I think another aspect is more accessibility, right? Right now, when we are talking about running on things, we are still you still need to be able to know how do you SSH into your embedded devices, or use GTAG to talk to your microcontroller and so on. Like if you talk to data scientists, they use Python and Jupyter notebooks. So we want to be able to really enable those people who just be able to do tinyML using the Jupyter notebooks, and for example, think about building infrastructure for them to easily build things and also gradually move pieces, right? As you develop things, originally you want to say that I want to put every part of my application on the device, but maybe you want to start by putting a layer first and gradually, move the things first, do debugging on your server machine if possible, then gradually move all that into the device so that make the development experience more smooth.
So I think that brings up a good point, TQ. You're kind of articulating a vision for what good looks like. Do other panelists kind of agree with this vision? Is that, is a Jupyter notebook, push a button?
I would actually try and take it. I agree with it. I think we can actually take the exciting things, we can take it even further. Like, the Magic Wand tutorial I was giving, earlier, on Monday, that's still using like Colab to train and like a Python notebook, and it's still using the Arduino. You have to sort of plug in the serial and deal with the serial driver debugging and all of that mess. What I'm hoping to do is actually get it working with Teachable Machine on the web page and use just a Bluetooth connection to like upload a trained model from like a web page, and in that way we kind of really have something that kids can just kind of, because the nice thing is if you can set things up so you can just gather training data and then everything else is automated, then you've got this really like no programming way for this vast audience of people to sort of train these models and really get into machine learning when they haven't even got into programming yet. So that's one of the things that really excites me about this stuff, and that's why one reason I think I give it a 2 is because I'm sort of thinking about that as the ideal state, is that it's not just, hey, engineers can use this, it's like anybody who's interested in kind of making a tiny little computer, do something useful for them can actually use this.
Yeah, I totally agree. I mean, I think it's really easy to forget that machine learning isn't, it's not a function, right? I think that what I would love to see is people taking AI techniques and using them as the best way to solve a problem. And the problem they're solving is they're building an application or an experience or, a solution for something, right? And when you start thinking about the broader picture of how you integrate these things together, it's not that AI is the thing, right? AI is one of the ingredients that you're using to solve a problem. and they're integrating it with the work loop of your application, and many of these other things like that become just unnecessarily complicated in today's stacks. And I think we can do a lot better in all these different places.
Okay, so we've talked a little bit about the where we are today and kind of this idea of where we could go in the future. What do we think the steps actually look like? So I come from a hardware background. I take great pleasure in complaining about software folks. What would you software folks like to complain about on the hardware side? What would make your lives easier? What step could the industry take on the hardware side to kind of get us to that vision of no programming ML?
Well, I mean, one of the things that is tricky with hardware, right, is that they provide different programmability capabilities, right? And I mean, whether it's a good reason or a poor reason, you probably know better. But that is one of the challenges that we have on the software side that we have to deal with, right? Because some of these low-level details about what the hardware is capable for, it basically affects all up to the stack, right? And I mean, one of the typical examples is quantization, right? Depending on what the hardware can really express, what the operations are available, is that I will, quantize my program differently, and potentially that, implies some significant changes to the original model. So that's one of the challenges that we have to face, I guess, on the software side, right? Like, how do we provide? Right now, I think perhaps also incorrectly is that we try to completely abstract, and maybe as a goal is a nice thing, but maybe we're not doing it correctly because basically the way that we try to abstract the hardware right now makes it really hard to make programs or adjustments to different hardware targets. So we are trying to strike this compromise that we haven't figured out how much to abstract the hardware, how much to let developers know to flexibly change it so they can target hardware better.
Pete, I'm interested in your thoughts on this. Do you agree with Raziel?
Yeah, I mean, honestly, the thing that's going through my head when you asked me about what hardware people could do to help us on the software side is actually just avoiding performance cliffs, because so much of the work around accelerators is, if you do, if you use exactly the ops that it supports, then things are going great. If not, then you sort of face like a round trip over some really slow bus back to the CPU to do something, and immediately all of your gains from using an accelerator are gone. And it's been really hard to, that's one big reason why we have these well-lit paths, is kind of we these paved roads, is we sort of have to go through, and for all of the major platforms, we sort of have to make sure that we're not, to use a different metaphor, like stepping on a landmine because we've, performance-wise, just because we're doing something that doesn't quite fit within the fast path of the hardware, and so the hardware just kind of throws up its hands, and we end up doing something super slow. It just doesn't work at all. We have what's hard to understand is we have people who are just bringing a massive variety of models and expecting them to work, and that sort of doesn't fit a lot of the hardware designs where they have optimized for 3 or 4 models and hope that that's all anybody will ever use.
Yeah, I think that there's a couple of things there. Raziel touched on the, can you separate the training from deployment completely problem? And I don't think you can. I think that if you want the best quality results, you need to do quantization-aware training, and you need to do other things where, you're not maybe obsessing about the target hardware, but you're at least aware of the target hardware. And this is where I think training platforms have a long ways to go. But you asked about hardware and complain about hardware people, and I love both sides. The challenge here, I think, is that people have been repeatedly solving the easy part of the problem, and so lay down and intate matmul, right? And so that's something that's easy to reach for. We understand what that does. We understand why it's accelerating the most important part of certain workloads and things like this. But then there's no reason not to make it more programmable. And I think that as you start looking at how hardware utilizes the the silicon, there's a lot of dead silicon that gets put down anyways. And so I think that this ratio of how much control logic versus compute that you put down, I think is really interesting. And it's not that there's one right space. I think that one of the sins that we have gone into as an industry is this notion of a kind of a one size fits none solution to problems. And there's a lot of vested interest in saying, you know, okay, buy my little hardware thingy. And it's perfect because I've done all the analysis and I know all of the different use cases and I've selected it for you as they handed down from, you know, the hardware gods way to solve these problems. But it's a vast ecosystem. There's a ton of trade-offs. And I think that, you know, the software folks, the compiler folks, and the systems folks need to make it more retargetable so that you can choose the right hardware given your use case. Also coming back to the fragmentation of the ecosystem that cuts against some of that. And so it's really kind of a dual-sided, we have to work together problem. On the one hand, we need software people to make it easier to have a more consistent deployment experience. On the other hand, we need to get hardware folks into more flexibility, more configurability, expose more control logic, some more programmability so you don't bounce back to the host, like Pete's saying, and like go off some huge performance cliff just because you want to do a sort or something, or top K or something like that. Right.
Interesting. So it's kind of this focusing on the easy part of the problem, you know, maybe the convolution aspect does naturally lead to these performance cliffs that Pete was talking about, and as well as kind of you lose that requirement for general programmability that Raziel was talking about.
Well, and it also holds back progress, is I think one of the things that bothers me the most, which is there's a huge amount of innovation in neural network architectures, and things are constantly changing. But if you can't deploy it, then it's just research, right? And so it's the gap between pure research and progress for the industry, I think, really comes down to deployability. And this is a combination of software, a combination of hardware, a combination of many different issues. But you know, if we continue to accelerate the matmul and cons only, we're like holding the industry back. And I think that that's not the ideal outcome. And I hope that, you know, in 5-10 years or something like that, we will have grown out of this.
TQ, your chance to complain about hardware people?
So I think I kind of agree with what others say about, you know, basically, you know, if we can get hardware to also looking into different problems. Another thing I think what's happening now is we need a more cross-stack mindset at this current moment. Like, for example, you know, when you are designing NPUs, actually in reality, people are not using NPU standalone, right? You want to think about how that interacts with the CPUs. How would your DMA bandwidth affects the potential, you know, if you are going to reuse both CPU and GPU on the same SoC. So I would say, basically, in a lot of cases, people need to go out of their silo of, you know, here's my boundaries, and I'm going to do well in my boundary, and leave the problem to other people. And another thing that I think is really interesting is that I do think things will become we are starting to talk about specialization, but there's also some question about how much programmability you want in the hardware itself, or you know, how much. Another thing is that because compiler, because the workload we're accelerating is still machine learning workload, so it's somewhat specialized. That means that the software or compiler runtime might be able to do more, which means that, you know, we might be able to, you know, create interesting hardware that do not be as smart as like a traditional CPUs. For example, you know, you could have something like explicit control dependency encoded in the instruction stream if necessary, as long as your software is able to do that. So that's also create quite a few interesting opportunities for the hardware. So one last thing that I think that's really excites me is about, you know, maybe having a more data-driven hardware development cycle. The idea is that, you know, even before you tape out your hardware, trying to directly put that into a compilation toolchain or a runtime toolchain that allows you to code simulate, so that you really know, like, what is the latest best model and how would they run into a hardware, as opposed to just looking at the standard benchmarks that people are looking at.
So that's interesting. You touched on benchmarks there, and that was, that came to my mind when Pete was talking about the performance cliffs, and how as an ecosystem or a community we can move forward and start to develop some reasoning about how to avoid those cliffs. Do we think benchmarks, getting behind some tinyML benchmarks to say this is actually what's important, is that kind of the right step forward? Or is that doomed to fail because the space is moving too fast and those benchmarks will be outdated by the time they take off?
There's a great effort underway in the MLPerf community to help standardize and drive some of this. Benchmarking is, in my opinion, an incredibly valuable thing because it helps unify the industry and provides a apples to apples comparison for different hardware and software and systems and tools ecosystems. The problem with it, as you point out, though, is that it's fundamentally a lagging indicator. Right? On the CPU side, for example, there's spec.
Yeah.
Right? And spec is well known to not be the perfect representation of most workloads, right? But it's something that remains super important and super useful if used the right way. And so I think that the best idea for an evolving world like AI is to both have a standardizing body like that and have a committee that really can cover all the different use cases, but then also keep turning the crank. Like, make sure it evolves and that it doesn't become a stagnant thing that's 8 years old that hasn't been updated.
Sorry, I just want to make sure. Raziel, did we lose you for a second, or are you back?
Yeah,
Okay.
I thought you kicked me out because I complained.
Yes, complain too much about quantization, people get kicked out of the panel. Yes. So Raziel, on your end, you think benchmarking could play an important role in helping to provide a forcing function for some uniformity of performance expectations across tinyML?
Yeah, I mean, I think it's one of the different tools that are missing in the stack that, again, is very important for researchers. So typically right now we see the research to production path, particularly for tinyML, as a sort of one-way street where we think that something is developed in the void on the research, and then somebody has to do magic passes to get it all the way to actually execute in production, particularly for small devices. And I think what researchers want is a tighter loop where researcher does something and they actually get some metrics that go beyond accuracy, right? They want to know what is going to be the power consumption, what is going to be the performance, and then I think hardware companies will get more direct feedback about what are really the needs that will bring all the way research, deployment closer together, and what are the things that really matter, what are the things that we could do different. Yeah.
So that's interesting. You just talked about that, and I think Chris touched on this a bit earlier as well. I think so. One approach that the community could take is we could try to abstract away the hardware such that on the research and iterative side, you don't really know much about the hardware or where you're deploying. That could be one approach. The other approach could be, well, maybe you need to have that hardware awareness on the training side and higher up the stack. Do we have opinions there? Is the kind of abstracting away the hardware doomed to fail? Do we need to kind of put that knowledge all the way up to the top of the stack?
I mean, I think I would look to analogies on this. So, from the old world of C, for example, right? C is an amazing hardware abstraction language for old school CPUs from the previous to AI world, right? But if you look at what C did, C allows you to standardize the vast majority of the code that you write, But if you're deploying to a microcontroller that doesn't have double precision arithmetic and you end up in soft float land, right, your performance will fall off a cliff. And so you have to kind of be aware of the data types that are supported. And I think the same thing will be true for all accelerators everywhere. The thing that I love about C that people usually don't talk about, though, is that C as an abstraction layer has inline assembly, right? And so from that world, right, you both get the ability to do hardware abstraction for the majority case, but then you can still get peak performance. And to me, I think that's where I look to in this world, as just by analogy, is, we can make it so things work, but you may fall off a performance cliff if you're using something that the hardware wasn't designed for. Fine, I think that's inherent. But what we should do is look to standardize and provide portability for the vastly most common cases, and then allow people to tune and get peak performance when they need it. And that gives you the bulk of the benefit without lying to people and setting people up for a promise that you can't deliver on.
I think it's sorry. Go ahead.
So go ahead, Raviel.
Oh, I was just gonna say that it is very true, right? Like at the end of the day, sure, this is machine learning, it's AI, it sounds fancy, but it's a software development problem, right? It's how you layer your solution, right? Like for a good amount of people or for initial experimentation, maybe a higher level layer that abstracts the hardware is fine. But then when you want to go deeper, then you should be able to do it, right? In a way that is not an all or nothing situation, right? Like Chris was saying, right? Like you can write C and then you can go crazier, right? And use special APIs or write your own assembly, right? You should be able to do that with machine learning frameworks as well.
And like I was just going to say, I think one thing that often gets missed is people treat the training side of models as kind of, oh, they're these neutral like constructs, but actually everybody's writing their models for NVIDIA GPUs because that's what everybody, the vast majority of people are training on. So what people I think miss from the training side is they have this nice kind of monoculture effectively that like makes a lot of things very, very easy because you can just kind of rely on a model that works well, kind of just working well across this range of NVIDIA GPUs. And really where a lot of the embedded and mobile stuff is, we're sort of, like I think Chris said earlier, we're starting to see this more even on the server data center side, where as soon as you start getting heterogeneous hardware in there, suddenly all of these models that you thought were going to be great fall down all these different performance holes. And we're just sort of part of that larger picture where people have for years been, ever since Alex Krzyzewski have been like writing models that run really well on specific NVIDIA GPUs, and then kind of treating it as if they're sort of, just carved in stone and just passed down to the rest of the world like they're just the sort of, the standard models, when in fact there's a lot of kind of opinionated stuff that has gone into designing those models so that they can actually train in a reasonable amount of time. And I'm not really sure what my point is with that, but it feels, it feels worth, pointing out.
I think actually, sorry, the point that you're making is very interesting for ML because in reality, we write two programs. And that is a very tricky thing. We write a training program and we write an inference program. And they are not necessarily the same program, right? We treat them as the same program, right? But really, even beyond, I think, what optimizations you can do automatically, you need some of the information that right now is not in the program to know how you want to actually run the inference on it. I mean, a simple case is you do batches, right, and training, which typically you will not use the batch dimension on inference, right? And then you can write entire chunks of computation based on the knowledge that on inference you're using batch 1, for example, right? Or for training you may do sequences that are like a particular fixed size, but on deployment there are going to be streaming applications where the sequence dimension is infinite, right? So this is a very very tricky thing that I think machine learning frameworks haven't gotten a really good solution because it's really hard. But it's one of the challenges of actually going from the thing that you train and the thing that you deploy.
I think this is a really interesting insight here, Pete. And I guess kind of reading between the lines, are you saying that, you know, neural networks often may have the shape that they do today and the behavior they do today, but that could be an artifact of the platforms that they're actually created on because they're optimized for these NVIDIA GPUs. And then so to take that, you know, that's why they look the way they do, and to expect them to kind of work anywhere else well is a big ask.
Well, I mean, let me give you an alternate view of the world that doesn't exist but could theoretically, right? I mean, so today people write models against NVIDIA GPUs, as people were talking about, running on CUDA and other things like that were tuned for benchmarks to make NVIDIA GPUs look good. Okay, and so, but if you're deploying to an IoT device, right, what you care about is building a model that then runs well for your users on that device. And so instead of being training centric, if you're deployment centric, then I think that what the world should or could look like, but doesn't, is you say, okay, well, I am, you know, training with a device deployment profile of that device. And so the kernels that I'm using for my training hardware, whatever it is, are not optimized to make ResNet 50 run fast on that training hardware. They're optimized so that when I quantize, they will quantize well to the deployment target. Right, and these may be completely different kernels. These may be using completely different D types that are not supported as well on the training hardware. But at the end of the day, you know, spending 30% more cycles during training to get a much better quality model at the end that you can deploy, I think is completely worth it. And the issue here is one of fragmentation of the ecosystem. So you don't have a compiler framework that can run the kernel that you're going to eventually deploy on the training hardware. Right, with the quantization rules that the deployment hardware uses on your training device, combined with the fact that like the incentives for the companies to optimize for their hardware are really strong, right? And the incentives to make it deployable on somebody else's hardware aren't really there. And so, but that's a a sign to me of an immature field, right? I think this is something that I hope and I expect that will grow out of over the course of years. Because there's nothing from a technology perspective that prevents us from solving that.
I think it's also an accessibility problem in a sense that people are nowadays there are a lot of researchers on how do you do binarization or quantization and so on. On the other hand, a lot of research nowadays are also not directly reflective. Like if you try to run most of binary network research literature, you'll find that they wouldn't run well on embedded devices because they are using floating point for batch norm, which basically kills their performance. I think the key bottleneck here is actually we still lack a push button tool that allows you to take your model or majority of model directly go even do some form of automation to search the kernel and directly run it on your target hardware to give you that direct feedback. And this is a lot. I know there are a lot of communities like ML community and TVM communities actually trying to push in for on this level of automation. And I believe this is very important. One observation that we find in OctoML is that when we try to benchmark like a standard benchmark like models that are publicly available and some of the models that our customer give us, what we found is that if you use automated solution, a lot of cases we get better on those private models because if you talk to those hardware engineers, NVIDIA or other companies, they are go and optimize for those benchmarks, right? So there's always a chance of overfitting the benchmarks. So benchmarks are important, but I think it's also important to also making the tools to be accessible. So those who are training machine learning models now have a way to directly go and try things out and see what is the end result, as opposed to going through several hops of cycles and people in order to really get it deployed. Once we get that fast feedback loop, I think this rate of innovation is going to be much faster.
That's super interesting, TQ, and so I think and I think Chris captured this, and I believe that the phrase, correct me if I'm wrong, Chris, was you kind of said deployment-centric training. That's kind of what is needed here. So, we started the panel talking about how the ML software inference is kind of stuck in the middle between the Cambrian explosion of hardware plus the dynamic research space of the training frameworks. And it sounds like, I think, a potential future is, a maturation of the hardware to avoid those kind of glass jaws or performance cliffs, coupled with, moving that research space towards a more deployment-centric view with some of the tools like TQ was just articulating. Is that kind of where we think it's going, or is that not is that not the right direction? Should we be thinking of something else?
So maybe if I can jump in just to make it more concrete, I think that the one massive obstacle at the moment is that the people who author the models tend to be ML researchers or trained as ML researchers. They are usually completely uninterested in retraining to help deployment. Like, there's very much that sense of, okay, my evaluation loop gives me like a 97% top one accuracy, throw it over the wall to those people who do the deployment. That's their problem now. And that's kind of like a social, kind of like a person problem. So when we talk about making stuff more deployment centric, it's like, how do we actually either persuade those people to be more interested in deployment, or kind of get people in who are model authors but not researchers at heart?
Or come back to Ian's original point of maybe the hardware people are doing it all wrong. And maybe what we need to do is acknowledge the way the world actually works, and instead of deploying, building deployment solutions optimized for benchmarks that are unusable, maybe we should deploy for, optimize for deployability.
Well, should we all just use Jetson Nanos? That's
if you have the power budget, I suppose.
I would like to be, I guess, more optimistic here and argue that researchers are not interested because the friction to be interested is large, right? Basically, if we get to the point where a framework can provide feedback about deployment as easily as they can get, or easier than they can get accuracy numbers, right? I think there is going to be, more of a desire to show that you can do better, not only on the accuracy side, right, but also in all these other metrics, right, that will become more and more important, because those are the ones tied to actually deploying and getting your thing used. And in a way, you kind of see that in some research papers, right? And the metric that we typically been using rather incorrectly is, how many ops does the model do, right? Like, we typically just, declare, oh, this model is smaller, right? It uses, 0% less parameters and, uses 50% less operations, right? Because that's really the best metrics that we have, right? And we know, right? We should know that there are not a translation of performance really in reality, right? But that's all there is. So that's what we are, standardizing on. So if there was a, better supporting frameworks to provide these metrics, then I think there will be more interest on doing research for them.
Yeah, I kind of agree with Raziel. It's more like a accessibility problem. Like, you need to make the toolings to be really accessible to those who only run Python. And once you have nice Python libraries to do a lot of these things will become easier. Another thing I think is important is also community-wise. Like, we will also need to cultivate a community who have that mindset. And for example, a more recent interest in the MLSys or machine learning system community is kind of like one such example community that cares both about the machine learning implications as well as like deployment of system implications. And we start to see a lot of interesting research coming out from that community that are quite relevant to what we care about.
That's actually a very, very interesting point, TQ. And I think, what folks just hit on here was that for this kind of gap to be bridged, we need this kind of accessibility. We need this kind of easy knowledge of deployment on the training side. And things have kind of naturally gone down. Well, there's the tinyML path that's all about inference, and then there's the researcher guys over here. And we're going to need these kind of things like MLSys or more systems based communities to kind of bridge those gaps. Okay, so we have a little bit more time. I think before we go into questions, I would like to, so let's just assume that each one of us gets one of Pete's magic wands, and we can fix one thing about the deployment problem with the magic wand. We can wave it and we can fix that one thing. What would be the one thing to fix? So I'm putting folks a bit on the spot here, but TQ, you're up on the page. Do you want to go first? What would be the one thing you would fix today?
Yeah, I think that would be basically the Python basically the direct Python deployment experience that I talk about. I think that is something that we really need, and maybe also a push button deployment. As I say, in before, when you push a button, you only deploy to one Arduino device with a lot of effort going on. But can you do that with the push button? Can you deploy to 3 kind of devices in a concurrent way, or 10 devices or 20 devices, and immediately get that feedback? I think that is a very exciting future that I would like to see. Yeah.
Raziel, what would you fix with the magic wand?
Magic wand. It would really have to be magic. I guess a core set of low-level operators from which we can compose basically express the majority of models for the majority of hardware. That would be my wish.
Very interesting. Pete?
So my wish would be having really solid feedback when you're at model creation time about what the model you're creating means for deployment. So which ops are supported, what the performance is going to be like, what the RAM usage, the flash usage, like all of that stuff. Because I think, like some people were saying, if we could actually bring that into the I was being unfair to researchers. They are interested in this stuff. It's just so hard at the moment that they've got no avenue to do this. If they could actually experiment a lot more easily, and just generally, if we could give people tools to help them create models and get feedback immediately, that's so much better than going through the whole training process, then trying to desperately export something and hitting all sorts of roadblocks.
And Chris?
I want something that obviously will never happen, but I will say it anyways. What I want is all the people that are working on these training frameworks to all give each other a big group hug, work together instead of fighting each other in a battle that doesn't actually matter. And if we can get the training frameworks to pull together the communities and actually work together, I think that the whole industry will move faster. And it seems unlikely, but if I had one wish, that would be it.
That's great. And actually, I had that question down. I'd avoided it, but let's just jump right into it since you brought it up. Are we forever going to have 2 different competing training stacks, or is there a future where these things could be merged? Raziel?
Well, I mean, I've I've seen both frameworks, right? Like at the end of the day, I mean, I don't think there is, we're both on both sides, right? We're trying to do the right thing. I think it's tricky, because right, like the goals of one or the other and the priorities may not be, exactly the same. Even though we, at a high level, we have the same like high level wishes of making, machine learning AI better and getting, research closer to production and make it faster and stuff. I think a lot of it will come to defining like good entry points that, if we can agree on them and we allow better interoperability, that might be a reasonable thing to do, right? We don't necessarily have to align on the same priorities or on the same solutions, but if at least we make some of these things interoperable between each other, then that would be a good thing. That's why I was, referring to, it's like, do we have a common set of operators that not only aligns frameworks but also hardware, right? That's why it was a big wish, because right, like that's an entry point, right? That's an entry point that we all struggle, right? Like frameworks, we implement a library of operators. And hardware, right? They define also their library of operators, right? There is no agreement on that entry point, so there's a lot of friction when you want to go from one world to the other one, right? Let it be horizontal or vertical, right? So that's the way I think about it.
And I would agree, and I think that what Raziel was saying about having a comparatively small set of ops that runs most models across most hardware is really the dream. And I think that, both TVM and MLIR and, the TensorFlow-like kernels that we sort of work on, I think at the engineering level, I guess we'd all love to, and I know the hardware people would love to get to that world where we have that, nobody really wants to innovate in like writing yet another reference implementation of conv2d because the padding is slightly different between one version and another. Like we want to be working on stuff that's actually moving things forward. The thing I see that's really hurting us right now is that we have so many ops that are continually being added by people creating new models. We have 2,000 plus ops in TensorFlow, and that number just keeps growing. A bunch of them aren't easily representable as kind of, from mathematical primitives. Some of them are, a lot of the most important ones are, but it's just this big soup of all of these different ops, and like understanding the semantics and trying to deal with them is what I feel really is holding us back.
I think it's I don't personally foresee a short-term merging of frameworks or anything like that. But Pete, I think that the point you're pointing out about TensorFlow is also a very specific to TensorFlow problem, where due to its history with graphs and using TensorFlow as a distribution format, it kind of went down the path of trying to re-encode all the world's computation into TensorFlow graphs, and so of course you get 2,000 ops and atomics and like all this crazy stuff that never really should be in an ML framework. I agree with the others. I think that commonizing the infrastructure is the next logical step. I think that TVM and MLIR and pulling more compilers into the world in general will help us get there. And then when you have, I think the innovation at the offset is actually a good thing. I think we want that. I think that we just want to get more hardware portability and more compilery things into the ecosystem so that the innovation doesn't paint us into corners.
Yeah, and oh, sorry, go ahead. No, I mean, I was just gonna say, I agree. The particular 2,000 plus ops is definitely a legacy of the design choices in TensorFlow. The tricky thing, though, that I see is like a lot of models depend on a whole bunch of like business logic or glue code that has to go somewhere. And if it doesn't kind of go in the model ops, then it gets very hard to figure out how you take a model and transfer it wholesale over to a completely different system that, for example, doesn't have a Python interpreter, or doesn't have a lot of the. So there's this it's the incarnation in TensorFlow of this problem is the number of ops, but the fact that you need all of this kind of around to kind of make what looks like at the heart a very simple numerical model to run is what seems to keep giving headaches to everyone.
History definitely has a Python problem. I agree.
Yes.
It's not a good thing for deployment.
All right, I think we are running out of time. I want to leave a little bit of time for questions, but before we dive into the questions, I'm going to clap for the panelists for the entirety of tinyML. That was absolutely fantastic, very stimulating. Okay, pulling up the questions right now. Yeah, so here's a question. Given the discussion about kind of deployment-centric approaches on the training side, is there an advice or path around moving towards kind of a bottom-up approach for deploying models? So a lot of the work now is taking these existing models that come out of the research space and squeezing down to a device. What about starting for something small? Approach. Anybody want to dive in? I could pick somebody, or
I mean, I think it's hard, or at least I don't fully understand how to start like backwards, right? Like at the end of the day, I think the way that I see the cycle is you have a problem, right? That in this case, like Chris was saying, right, you happen to want to have a solution that is built around AI, ML, right? And it kind of starts from the top, and then, right, like, yeah, I mean, basically, first you kind of find a solution, and I think it doesn't have to be also entirely so like top down as it is right now. Right now it's very top heavy, but I don't necessarily see it going like completely backwards, right? Like,
yeah.
And also I don't think it's the right thing to do, right? Like I think we want a balance, not like top heavy or bottom heavy.
What about, so here's a question. Do we have, for the hardware folks in the audience building stuff, do we have tips, or where should they go and look to make sure they're building something that is friendly towards the modern networks?
I can take that one. So I think the first thing that I would do is think about software actually when you are building hardware instead of just focusing on hardware. So maybe like we start to see examples, when people design hardware, start to hook simulators or cycle models onto compiler backend so that you can directly say how your PyTorch or other models of interest run, and use that to drive the design process. And that will be certainly more informative than just working out a few benchmark models like manually.
Yeah. Okay, great. I think we are out of time. I want to thank the panelists again. That was great. So thank you all very much.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. ADA Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse, EMSA, Gray Matter Labs, Green Waves, HiMax, Imagimob, Latent AI, Maxim Integrated, Quixo, Reality AI, SensiML, Silicon Labs, Sentient, Google TensorFlow, XMOS, and lastly, silver sponsors, Edge Cortex, Hotchi, and SynSense.